In this video, I'm going to be talking about differential amplifiers. And so I'm going to briefly talk about how differential amplifiers are set up, and then we're going to dig into how they behave in small signal analysis. So what I have is two MOSFETs here, which are set across from each other, connected by their source to a current source, which has a value I, and a power supply negative VSS. And what I'm going to do is I'm going to input voltages into the gates. So that's V gate 1 and V gate 2, and I have outputs V drain 1 and V drain 2. And it turns out that by changing V gate 1 and V gate 2, I'm able to change the value of the current through each of those transistors. And the characteristic of that current is shown over on the right hand side here. So for the second transistor, the current is going to range from its full value down to 0 by changing the value of the differential input voltage. Differential input voltage is going to be the value of each of these gates subtracted across from each other. The place at which it reaches 0 is the square root of 2 times the overdrive voltage, which is just the square root of 2 when I normalize by dividing by V overdrive. And so I can essentially, by changing those voltages, switch the current from one side to the other. The current ID1 is equal to the biasing current big I over 2 plus I over V overdrive times V input differential over 2 multiplied by the square root of 1 minus VID over 2 over V overdrive squared. And ID2 is the same thing, except instead of adding all of that second half, I'm going to subtract. So let's drill a little more deeply into this. The input differential voltage is V gate 1 minus V gate 2, which is V input differential. That's equal to V common mode plus 1/2 VID minus V common mode minus 1/2 VID. So it's a total of VID, my input differential voltage. And the output differential is measured between the drain of the right-hand transistor and the drain of the left-hand transistor, Q2 and Q1. That's my output differential voltage, VOD. So let's convert that into the small signal model. And what I have is I'm going to replace this transistor with its T model. So I've got the input at the gate here, V gate to source 1, and then I've got a resistor 1 over GM and a dependent current source, GM times VID over 2. And that's what happens for both of the transistors. It just so happens that at the left-hand transistor, Q1, I've got an input value VID over 2, and at the right hand, I get negative VID over 2. The common modes will cancel each other. Then the voltage at drain 1 is negative GM RD VID over 2. The voltage at drain 2 is positive GM RD VID over 2. These come by taking that current source multiplied by my drain resistance. And so when I take the differential value, I remove the divided by 2 and I get GM RD times the differential input voltage. So let's look at that mathematically. So the transconductance GM is generally in a MOSFET transistor circuit 2 times ID over V overdrive, which is actually equal to 2 times the bias current I over 2 over V overdrive, which is equal to just the bias current I over V overdrive. I've already established that VD1 is equal to negative GM VID over 2 times RD. That's the dependent current source multiplied by the resistance. So there's a voltage here that I'm getting. And then I also know that VD2 is positive GM VID over 2 times RD. And so if I take VD1 over VID, I get negative GMRD over 2. And if I take VD2 over VID, I get GMRD over 2. And so the actual differential gain, A sub D, is VD output differential over V input differential, which is equal to VD2 minus VD1 over VID, which is equal to GM times RD. So that's my differential gain for this system. Now, there are some advantages of differential amplifiers. The first advantage is that a signal ground can be established without a large bypass capacitor, which is very important in integrated circuits. The second advantage is that by taking the output differentially, we can increase the gain by a factor of 2 instead of taking it single-ended. However, there is one disadvantage that I want to mention, which is that some applications require single-ended outputs. Okay, so I'd like to do two quick examples. In the first example, I have a MOS differential pair biased with a current I, which is 200 microamps, and it is found to completely switch the currents from one side of the pair to the other when VID is 0.3 volts. What I want you to do is first find the overdrive voltage which makes this happen. Now, if the differential input voltage for full current switching needs to be 0.5 volts, what should the bias current change to? So to solve this, let's look at the first part. I want to find the overdrive voltage if VID is 0.3 for full current switching. I know that switching occurs when VID is equal to the square root of 2 V overdrive. Just from the beginning of this video, I saw that. In fact, let's zip up for a minute. So I can see at square root of 2 V overdrive or negative square root of 2 V overdrive, that's where I switch from one side to the other. Okay, so all I've got to do is take 0.3 divided by the square root of 2 to get V overdrive. That's equal to 0.212 volts. That's V overdrive. The next thing I want to do is I want to find out what the bias current should be to give me a different switching, which means I need a different overdrive voltage. So V overdrive new over the one I just found, which is 0.212, has to be the same ratio as 0.5 to 0.3, 0.5 being the differential input voltage I want, 0.3 being the one that I already have. So that means that the new V overdrive is equal to 0.212 times 0.5 over 0.3. So that's like 1.66 times 0.212. So this is equal to 0.353 volts. And I know that ID is proportional to V overdrive squared. So what that means is that big I should be equal to 0.353 over the original overdrive voltage, 0.212 squared, times the original current, which was 200 microamps. And when I multiply this out, I get 554.5 microamps. And that's that example. In the second example, I'd like to design a MOS differential amplifier to operate at an overdrive voltage of 0.25 volts and provide a transconductance GM is equal to 1 milliamps per volt. In order to do this, I need to specify the width to length aspect ratio and the bias current, big I, if the turn-on voltage for my transistor is 0.5 volts and mu in COX is 400 microamps per volt squared. Okay, the first thing that I know is that GM is equal to 2 times big I over 2 over V overdrive, which is the same as big I over V overdrive. And I know that I want this to be equal to 1 milliamp. And I also know what I want V overdrive to be. So if V overdrive is 0.25 volts, then that means that 0.25 times 1 mil is equal to big I, which is equal to 250 microamps. If I assume that the transistors are set so that way the differential input voltage is 0, then I know that ID for either transistor is just I over 2, which is equal to 1/2 mu in COX, oxide capacitance, aspect ratio, V overdrive squared. And I know all of the information about this except for the width to length ratio, the aspect ratio. So width to length aspect ratio is I divided by mu n cox v overdrive squared. And if I plug in values, that's 250 microamps over 400 micro, and this is 0.25 quantity squared. And when I do that, I get 10. So that's the ratio that I'm looking for. And that is my final answer. I needed the aspect ratio and the bias current. I found both things. And that is an example of doing amplifier design with a differential pair. Check out other videos on my channel if you want to learn about other electronics or electrical engineering content. That's all for now. Thanks for watching.